Good morning. Today we are going to continue tackling Chapter 5, which deals with metal oxide semiconductor field effect transistors. In the previous lectures, we talked about the linear region of operation for the MOSFET, the triode, the saturation regions, what those mean. And today we're going to really just dive into a bunch of examples, which I think is a very important part of this chapter. As the material becomes more difficult, it becomes more important to spend more time dealing with examples. And this will lead us into next lecture, Friday's lecture, where we will do a few more examples, but more importantly, start talking about how we can use MOSFETs to design operational amplifiers, which is really one of the key takeaways from this class. Good morning, everyone. We are still in Chapter 5. We're talking about the metal oxide semiconductor field effect transistor. And as usual, we'll pick up a little bit before where we left off last time, just to give a little bit of review. I thought one really good place to start would be Table 5.1, which provides such a great overview of how the NMOS transistor works and really summarizes so many different parts of of what we learned, right? Here you have a basic circuit configuration with your VGS. You have a voltage VDS applied across the drain and source terminals, shows where your ID is. You have your VI characteristic right here, showing clearly the saturation and the triode regions, as well as the boundary between those two where VDS is equal to VOV. We also see the linear region down here, for which a constant RDS value is defined. It provides us equations for the triode region as well as the saturation region. Anyway, this is a really great table to understand. Really great for a quiz or an exam. I mean, overall, it just provides such a great, concise overview of everything. If you understand this, I feel like you really understand the NMOS transistor. And I don't know if we've presented the table yet for the PMOS. We either did or we will in a second, and it provides a similar level of summary. I think we did look at this graph last time, and what it shows is two different things. Number one, right, you do have different VI curves as your value of VGS changes, which is also proportional to VOV, which will increase the ID value, at least for this NMOS enhancement type transistor that we're talking about. It also causes the transition point to move to the right as we go upward. So one topic that we're going to be talking about, I think today, we will get to that, is how to implement op amps using the MOSFET. And so when we use the MOSFET to implement an amplifier, in what range will they be operated? They'll be operated in the saturation region, and we'll talk more about why that is. In the saturation region, the drain current is dependent on VGS, but it's independent of VDS. And that's reflected by the fact that the slope here is 0, right? There is no effect of VDS, which is on the x-axis, on ID. So in effect, it becomes a voltage-controlled current source. So our MOSFET will look like a voltage-controlled current source. So this will be K times V in, and this will be V in right here. Okay, so like we said before, it becomes a voltage-controlled current source. This is a key characteristic for amplification, and this is shown in equation 521. Equation 521 is simply just the VI characteristic for the saturation region. We've seen this a bunch of times before. And one problem with 521 is that it's nonlinear, right? We ideally want a constant slope here because we want our gain to be constant. Unfortunately, that is not the case with the MOSFET. And so that's something that we will need to overcome, or we will need to correct for, in order to get the type of operation that we want. So on this slide, we are going to look at the transistor as a voltage-controlled current source. This circuit is known as the large signal equivalent circuit. We'll talk in a minute about why that is. The current source is ideal. Both the input and the output resistances are infinite. You can see our input resistance would be right here. Our output resistance is right here. Both are infinite, which means there's no current flowing into our transistor, and there's no shunt current flowing here. So ID is equal to the equation as it's written right here. I apologize for the extra markup. Unfortunately, I'm not able to figure out how to erase once I write on the PowerPoint slides. So note that in this circuit, ID is completely independent of VDS, and that's again because we've assumed that there's no shunt resistor, or that the resistance there is infinite. Okay, so let's take a look at another example. This is example 5.2. We want to consider an NMOS transistor fabricated using a 0.18 micrometer process. The channel length is here, the channel width is here. The process technology is specified to have an oxide capacitance of 8.6 femtofarads per micrometer squared and a mobility of 450 centimeters squared per volt second. And then the threshold value is 0.5 volts. It asks us to find the value of VGS and VDS that result in the MOSFET operating at the edge of saturation with ID, that's the same as I sub D, equal to 100 microamps. And then we'll talk about the other two parts in a second. So the first question I want to ask is really a question we are going to ask over and over. Which equation do we use for the problem, for any problem that we're taking a look at? We have several different equations. We have the linear region, we have the nonlinear triode region, we have the saturation region. And so solving the problem becomes a lot easier once we figure out which equation it is that we're going to use. Here they tell us we're at the edge of saturation. Now, edge of saturation is really the same as saying the edge of saturation and triode. So at that boundary, both equations should work. Normally, we are going to choose the saturation region equation because, we'll see in a second, that has fewer variables that we have to deal with. So the first step is to calculate the transconductance parameter for the NMOS using this equation shown here. I'm not sure why I wrote 521 and then 511, but I think it's equation 511. And right, we have our mobility, we have our oxide capacitance, and there's not too much difficulty here if we assume that we know how to take care of the units. And so you can see I've been pretty careful to show how to account for the units. Right, 1 farad is equal to 10 to the 15 femtofarads. 10 to the 6 micrometers is equal to 1 meter. But since that unit is squared, we have to square this whole thing. So if you're not familiar with how to properly handle units, I really recommend you take a look at this more closely. It seems like it's a no-brainer, but again, this can be the details that you miss that prevent you from getting the correct answer to a given problem. Anyway, real quick, before I move on, right, the value we get for the process transconductance parameter is 387 microamps per volt squared. And if we wanted to get the device transconductance parameter, that would be 387 microamps per volt squared times the aspect ratio. Remember, that's the difference between Kn prime and Kn. Okay, that's what we do next. So we calculate the device transconductance parameter. And then now what we're going to do is define ID and set it equal to the 100 microamps. Like I said before, we know that we're at the boundary of triode and saturation. which they call the edge of saturation, same thing. And so we can use the equation for the saturation region, which again only has one variable to solve for, which makes it easier. The triode region expression is dependent on both VDS and VOV, which makes it more difficult. There's one more variable to deal with. So anyway, what we're going to do is we're going to solve this for VOV. In order to do that, we simply take, we move the variables over to the other side using division. We take the square root, and so we end up with 215 millivolts as our overdrive voltage. Next. So specifically what it asks us for in this problem are VGS and VDS. So we need to convert between VOV and VGS. We know that VOV is equal to VGS minus the threshold voltage. The threshold voltage is given to us as 500 millivolts. We know our overdrive voltage is 215.7 millivolts. We got that in the previous part of the problem. And so all we did to go from here to here was rearrange part of that equation. So VGS is equal to the overdrive voltage plus the threshold, those two together, and that gives us 715.7 millivolts. So that's one piece, that's one part of the answer. The second part of the answer is asking for VDS. And so we know, because it tells us we're at the edge of saturation and triode, that VDS is equal to VOV. That is the definition of the threshold between the triode and the saturation regions. And therefore, VDS equals VOV equals 215.5 millivolts. So part A is answered. See if I can zoom in here to part B. If VGS is held constant, find the VDS that results in ID equaling 50 milliamps. So again, I'm going to ask the same question, which is going to be, which equation do we need to use? That is a constant question we're going to ask ourselves in these types of problems. All right. So, on the previous slide, VOV is calculated. Will this value change as VDS changes? No. And why is that? VOV represents the difference between VGS and VT. VGS doesn't change, and so VOV will stay the same. Because if you look at the way the problem states, it says, if VGS is kept constant, it says that very clearly. Find the VDS that results in yada, yada, yada. Okay, now, let's try to imagine what's going on here. So I'm going to draw this generic VI curve for the MOSFET. And let's look at where we were before. So before we were here. We were at the edge of triode and saturation, and that was where VDS is equal to VOV. They tell us VGS is held constant, which means we're not going to be jumping up or down to another VI curve. So we have to move somewhere along this VI curve. This is 100 microamps. This down here would be 50 microamps. So that means that would put us at that point right there. And so you can see very clearly from this picture that we know as we move towards this second point, we will be in the triode region of operation. So we know that we're moving to triode. As such, you'll see that the equation we have here is the one for the triode region of operation. And so now we're going to set this equal to 50 microamps. A lot of this stuff is already defined. This all right here is our Kn value. Then we have VOV minus 1/2 VDS. Anyway, the rest of the parts of the equation are all listed out. We know what VOV is. It's 215.5 millivolts. We don't know what the VDS is. Okay, so anyway, we plug in all the values that we have, and we end up with this equation right here. This, it may be difficult to see, but this is going to end up as a second order polynomial with the variable being VDS. So it'll look like something alpha VDS squared plus beta VDS plus some constant equals 0. So second order polynomial means that we can use the quadratic equation to solve. I didn't show that explicitly, but if we applied the quadratic formula, we would end up with two answers, as the quadratic formula will often provide: 6 millivolts and 390 millivolts. So first things first, we know that we're not going to have two answers over here. We're only going to have one. So we need to figure out which one is the right one. All right. So which one of it is correct? It must be 6 millivolts because 390 millivolts is larger than VOV and will signify saturation. So I'm going to go back to this picture right here. At this point, this was VDS was equal to approximately 215 millivolts. So we solved for two different values of VDS in the second part. One was 390, and the other was approximately 6 millivolts. So 390 is on the right-hand side of this, pushing further into saturation region. That cannot be the answer because we've already determined that it must be in triode. Therefore, the only answer that moves us to the left into the triode region is 6 millivolts, and therefore we know that this is the actual answer that we're looking for. So when we solve these types of problems, there's, let's say, 3 steps, okay? The first one is always going to be trying to figure out which equation we need to use. I've said that several times. Step number 2 is to solve and, do whatever algebra is required in order to solve. And then number 3, which is not always going to be the case, is going to check our answer or to make sure that it's coherent with Now, moving on to section 5.2.4, finite output resistance in saturation. In the previous section, we assumed that in saturation, ID was independent of VDS. And what we said was that a change in VDS caused no change in ID. This implies that the incremental resistance is infinite, and it's based on the idealization that once the N channel is pinched off, changes in VDS will have no effect on ID. The problem here is that in practice, this is not completely true. So let me draw all of these real quickly. So the assumptions we make, number 1, is that our VI curve looks like this, where the slope here is equal to 0 in the saturation region, right? That is one of these, it's part of this assumption here, that this slope is equal to 0. Another way of representing this assumption, when we draw the transistor as a voltage-controlled current source, okay, is that this resistance, output resistance, is equal to infinity, okay? The incremental resistance is infinite. And also, if I were to really quickly draw the MOSFET, and we have the channel. The channel starts off as a rectangle. It gets more and more trapezoidal. Then it eventually becomes a triangle. We have assumed so far that once it becomes a triangle, this point never starts to move to the left, which is called pinch off. So now what we're going to do is we had three versions of the same assumption. And in this next section, we are going to get rid of all of them, meaning that now we will have some effect ID will be a function of VDS even in the saturation region. Okay, so what effect will increased VDS have on the N channel once pinch-off has occurred? I remember I said we had this triangle, and so pinch-off is when this point starts to move to the left. So it will cause the pinch-off point to move slightly away from the drain source and create a new depletion region. The voltage across the now shorter channel will remain at VOV. However, the additional voltage applied at VDS will be seen across the new depletion region. So let's talk about that. So this voltage, this is still part of the same question, just more answers to that same question. This voltage accelerates electrons as they reach the drain end and sweeps them across the new depletion region. So again, we have, my drawings are getting poorer and poorer by the moment, but so we have a channel that no longer reaches all the way from the drain to the source because pinch-off has occurred, and the new depletion region is right in here. So the voltage accelerates electrons as they reach the drain end, sweeps them across, they reach the channel, and they keep moving. So the electrons are still able to move between the drain and the source, but the length of the N channel will decrease, and the decrease of this length right here, can't spell length, is known as channel length modulation. So what you'll see is that a lot of problems will say, consider channel length modulation versus don't consider channel length modulation. When we do consider channel length modulation, we are assuming this. We are going to get rid of all three of these assumptions when we do consider channel length modulation. When we don't, then this goes back to being flat, this goes back to being infinite, and this no longer moves to the left. All right. So we know physically what is happening, right? You can see here, this is the new depletion region. This is the gap between the drain and the channel. But how can we describe this mathematically? So you see here, equation 517 is the old equation we used for the saturation region. And now we have a new one that takes into account channel length modulation. It's the exact same equation, except now we have added this additional term, lambda VDS. And so, right, this is the fourth equation. I don't know if you remember, there was a slide maybe one or two classes ago where it was showing all the different models for the MOSFET, and I said we hadn't gotten to this one yet. Well, anyway, this is the one that we had not gotten to yet. Now, this is how you represent channel length modulation in the equation. And now if you want to represent it in the large signal equivalent model, we would take this RO, which used to be infinite but is no longer infinite, and give this a finite value. So how is RO defined? So far, what we have assumed is that the magnitude of the channel length modulation, or the effect of the channel length modulation, is given to us as this lambda value, which, right, if lambda is equal to 0, then we don't have any channel length modulation. If lambda is greater than 0 or non-zero, then we do. So how do we relate those back? So how do we define RO? Step number one is going to be to realize that the resistance is the derivative of the current with respect to the derivative of the voltage. That's the same as any, sorry, it's 1 over that, because really resistance is voltage divided by current. Right, that's the same way we could derive or define any resistance. All right. So now what we will do is we will take the partial derivative of ID with respect to VDS, and we're going to plug in the equation that takes into account channel length modulation with the lambda value. When we take the derivative of that, what we can see is, right, we can actually split this up into two parts. One part is all of this, which is constant, and the derivative of that with respect to VDS will be 0. And then the second part of it will be a coefficient of lambda VDS, and that's this right here. So this was originally multiplied by VDS. We take the derivative with respect to VDS, so it goes away, and we're left with the coefficient. 1/2 mu n COX aspect ratio VOV squared times lambda. So these three steps are enough for you to understand the derivative. If you need to go back and take a closer look, please do, and don't hesitate to ask me any questions. Anyway, so when we're done with that, what we see is that the output resistance is equal to 1 over 1/2 Kn prime aspect ratio VOV squared times lambda. If lambda is equal to 0, channel length modulation is not taken into account, and the RO would be infinite if lambda is equal to 0. All that makes sense. So there's three different ways we can define channel length modulation. We can define it with in terms of a lambda value. We can define it in terms of an R out value for the voltage controlled current source. And then lastly, we can define it in terms of this VA, which is shown right here. So what does VA represent? It represents this point here. So now the main difference we'll see between the VI curve with and without channel length modulation is that without channel length modulation, this is flat. With channel length modulation, it begins to ramp up. And so all of these lines will intersect at a point called negative VA, and that is equal to negative 1 over lambda. And so that provides us, you can see the relationship between VA, lambda, RO, three different ways of describing whether channel length modulation has an effect. So what is lambda? It's a device parameter with the units of 1 over volt. Okay, the value of which depends on the manufacturer's design and process. It's much larger for newer technologies. And right, when lambda equals 0, there is no channel length modulation, and when it's greater than 0, there is. So figure 517 demonstrates the effect of channel length modulation on the VI curves, and you can see that in the saturation region. I'm sorry, I feel like I'm being a little bit repetitive here, but in the saturation region, ID is affected by VDS. All right, let's move on. Characteristics of the P-channel MOSFET. I thought I blew that up, made that bigger, but I guess not. It's all summarized here. Like I said, at some point, whether it was last time or the time before, we are going to be focusing in this class on problems of the enhancement NMOS transistor. I'd rather get deeper into asking you problems about that and expecting you to understand the differences between the transistors, as opposed to just asking one of the same problem and rotating through all these different types. Okay, that being said, it does not mean you need to know nothing about depletion type transistors. It also doesn't mean that you need to know nothing about PMOS type transistors. So there could be written questions, short answer questions that ask you about the PMOS and how it works. Now, if you understand table 5.1, 5.2 is laid out in the exact same way. What does the basic test circuit look like? What does the VI curve look like? How do we define the behavior in the triode and saturation regions? So I think that, we do have one or two homework problems that deal with PMOS transistors. When you're dealing with the PMOS, a really great way is just to compare table 5.1 to table 5.2 and right, use those two together as a guide, right? You understand 5.1. You know what parts of 5.1 you will use, and so you just look for the corresponding parts in 5.2. Like I said, I'm not going to go into too much detail here. I mean, there are some major differences, right? You do need to apply a negative voltage in order to excite and create the channel between the drain and the source. And so that has lots of effects on the way that this thing works. For example, right, we are going to compare the value of VSD to the absolute magnitude of the overdrive voltage, because the overdrive voltage, right, all the values, the signs will be flipped. Anyway, I feel like the best way to address this is for you to take a look at table 5.2 and come to me with questions if you have them. Homework number 12 is assigned like usual. It will be quote unquote due a week after it's assigned. So this lecture is being given on April 14th, 2020. And so I would expect for you to have it done by April 21st, 2020, which is actually the day of the midterm. The second midterm. All right, so now moving on, MOSFET circuits for DC cases. Let's talk about how the MOSFET behaves in DC circuits. And we will neglect the effects of channel length modulation, assuming that lambda equals 0. It is an interesting way that the book treats this because they spend all that time talking about channel length modulation, and then they immediately jump to ignoring it for 90% of the problems. It makes sense in one regard. We have to be aware of what channel length modulation is, but we are not going to address it in a majority of problems. Anyway, so we are going to work in terms of the overdrive voltage, which reduces the need to distinguish between PMOS and NMOS transistors. What does this mean? So what it means is that the book, we can pose problems in terms of VOV, meaning solve for VOV, you're given VOV, and not ever asked to go and put that in terms of VGS or VSG. This will be required for the NMOS. This will be required for the PMOS. And so if you never take that extra step, it's actually, when you solve, it's irrelevant whether it's a PMOS or an NMOS. So that's what they're trying to say, is that for these problems, now we can even transcend this whole idea of worrying about whether it's a PMOS or an NMOS. Okay. Example 5.3, they still tell us it's an NMOS transistor. Design a circuit like that shown in 521. And so we want to determine the values of RD and RS such that the transistor operates with this equal to 400 microamps. VD is equal to 0.5 volts. And then the rest of the values are just given. So the threshold voltage, the process transconductance parameter, the channel length, the channel width. Again, neglect channel length modulation, so lambda equals 0. All right, so what's left? We need to figure out what is RD and what is RS, such that we satisfy these conditions. What's the first question we're going to ask ourselves? As usual, which equation do we need? Which region of operation are we in? Are we in saturation or are we in triode? Now, this problem, as far as I can see, doesn't tell us which one, and that means we are going to have to figure it out as we go. Okay. Now, there is some low-hanging fruit here. You see that we know what the voltage differential is here, right? This voltage difference between these 2 points is 2.0 volts, right? Because it goes from 2.5 to 0.5. And we also know what the ID value is, because it's the same up top. It's 400 microamps. So finding RD is going to be very easy. We know RD will be equal to 2.5 minus 0.5 over the 400 microamps, which gives us 5 kiloohms. Next step, determine, we want to define ID in terms of RS. So we got our RD, that's good. Next, we want to figure out what RS is. We try to set up an equation for that using KVL and Ohm's law. Unfortunately, we don't know what VS is. So this is not going to be as easy as this one. So this one was easy, and this one's going to be a little bit harder. All right, so what else do we know? How can we find VS perhaps from VGS? And this is a common strategy. You know, when we are dealing with a problem like this, and one equation doesn't give us doesn't isolate the variable that we're looking for, allow us to solve, we're going to ask ourselves, what other equations are out there that we can use? And so another one is the fact that VGS equals VG minus VS. And this below is just a rearrangement of what's shown. VG is ground. We're trying to figure out what VS is. Now let's ask ourselves, do we know what VGS is? And so, how can we get VGS? Maybe from VOV. Again, another equation that we have access to is the overdrive voltage is equal to the gate source voltage minus the threshold. These values are given to us, right? They tell us somewhere. Actually, no. They don't give us VOV. They give us VT. So this is where the problem starts to get hairy. Okay, we don't have VOV. Is there another equation that we know of that can perhaps give us VOV, which we can plug in back here, and then we can take VOV and get VGS and get VS. So we're looking at quite a weird chain here. We're trying to get VS from VGS, from VOV, and ultimately we're going to get that from ID. So, right, as you can see, a lot of different steps in trying to get this. All right. So this equation here, we're going to define the relationship between VOV and ID and solve for VOV. But how do we know, question I've asked several times, which equation? Okay, normally we're going to assume that's not in the linear region because the triode equation actually addresses the linear region anyway. They told us there's no channel length modulation, so we don't have to worry about that. So we're down to two equations, saturation or triode. What we're going to do here is we are going to assume saturation. And there's a reason for that. Number one is that we need to move forward. So we can assume an equation and check it later to see if our assumption is right. And why do we start off with saturation as opposed to triode is because, again, it's the equation that only has one independent variable. All right, so we're going to say ID is equal to 1/2 mu n COX aspect ratio VOV squared equals 400 milliamps. I highlighted that for some reason. Oh, I think there was a discrepancy between the value they gave in the problem definition and the book. That was why. All right. Well, the next time we go through these slides, well, you won't see it, but I'll fix that issue. Okay. So moving on, right, we have our VI characteristic in the saturation region. And now what we want to do is go back and solve for VOV. So we are going to move this piece to the other side. We're going to take the square root of all this. And anyway, once we get all the way to the bottom and we solve, we see that VOV is equal to 0.5 volts. So now we took this, we got a value of 0.5 volts right here. Our VGS will then be defined using this. VGS will be equal to the overdrive voltage plus the threshold. The threshold is 0.7. So that means that this will be 1.2 volts. And then lastly, if we go down to this equation right here, we know that Vs is equal to minus VGS plus 0. So Vs will be negative 1.2 volts. So you can see that was a way that we stepped that backwards. So I showed you how to do this, showed you how to do this. Now, let's go ahead and plug this into our equation for RS, which this was the only unknown. So we have minus 1.2 volts we subtract out a negative 2.5 volts, divided by our 400 milliamps. Now we do know Vs, and so that gives us an answer which is 3.25 kilo ohms. Now, one last thing which we did not do, but I would recommend, so I'll write it over here, is for the last example, we need to check and make sure that we really are in the saturation region, because the equation that we used was the saturation region equation. We have to make sure that was a good guess. So what we need to make sure is VDS greater than VOV? So our VOV for this case was 0.5 volts. And our VDS, let's see where we can get that from. So VD was given to us in the beginning as 0.5. So I'll write that down. So 0.5 volts minus our Vs, which we have at the very end. So that's minus a negative 1.2 volts. So that gives us 1.7 volts is greater than 0.5 volts. That is a constraint that we satisfy. And so we are in saturation region, and we can keep our answer. Now, if that inequality was not satisfied, then we would have a problem. We would have to go back and redo the problem using the triode region of operation equation. Fortunately, that's not the case. Example 5.5. So a lot of examples in this chapter, more so than chapter 4 or chapter 3. And I think as we get into more difficult material, that's important. We'll focus more on the homework. We'll focus more on examples, and it takes more practice to understand these types of problems. So I think it's a good thing that there are more examples. So jumping into the next one, example 5.5, design a circuit as shown in figure 5.23 to establish a drain voltage of 0.1 volts. So this is a constraint we're trying to meet. What is the effective resistance between the drain and the source at this operating point? So this is Vs. Vd is already given. And so we're trying to figure out what this equivalent resistance would be, which would be RDS. And then they give us some parameters as usual. Okay. First question we're going to ask ourselves, which equation do we need to use? Which region of operation are we in? Always going to ask ourselves that question. All right. So I'm going to skip this equation for 1 second, because really trying to figure out what RDS is before we know what the current is, it's not going to work. Okay. So the good news is we do know what region of operation it is in. So the MOSFET is operating in the triode region because VGD is greater than VTN. This is just another version of the equation VDS is greater than VOV. We can do it the traditional way if you want. So we know, let's calculate VOV real quick. So VOV will be VGS minus VT. The VGS is going to be 5 volts as shown here. Minus 1 volt. And then, so that's 4 volts. Our VDS is going to be 0.1 volt minus 0, so 0.1 volts. And so you can clearly see that VDS is going to be less than VOV, which means we are in the triode region of operation. So we can answer this question, which is nice. Triode region of operation, which means we have to use this equation here. Now, a lot of these values are given to us. In fact, all of them are. We know the device transconductance parameter, Kn. We know the overdrive voltage is 4 volts. We know that VDS is 0.1 volts. We just stated all those values, and so we can go ahead and just plug those in, and that'll give us a value of ID, which is 0.395 milliamps. And then now we can plug that into this equation down here, which simply just says, so the resistance RDS will be equal to, go all the way back here, it will be equal to VDD over the sum of the two resistances together, or you could say VD over ID. So which one do we use? Let's see. Whoops. So let's see which one we use. So it looks like we're going to, what is this? Hold on, RD. Okay, so first it's calculating the RD value, which is going to be 5 minus 0.1 over whatever the ID value is. Okay, so that's what we're calculating first. So RD is equal to 12.4 kiloohms. And then we can figure out what the value of RDS is using, again, a similar sort of KCL Ohm's law-based equation. RDS will be equal. So you could do it this way. Honestly, I would say it's easier just to say that RDS is equal to 0.1 volts minus 0 over the 0.395 milliamps. You don't really need to calculate RD in order to get RDS. And that will give you the same answer, which is 253 ohms. Okay, so example 5.6 is, you can see we're slowly getting into more and more complex examples, more resistors, a little bit more complexity. So I think this will be the last example that we'll take a look at, and it'll be a nice stopping point for next time. So example 5.6, again, another MOSFET one. We want to analyze the circuit shown below to determine all the voltages at all the nodes and the current flowing through all the branches of this circuit. All right. So you can see here I have an unlabeled version of the circuit, and then I have a labeled version. You can see there's some stuff that we can really pick off very easily off the bat. We always know that the current flowing here is going to be 0 for a DC system at least. Therefore, these two together are going to work like a voltage divider, and so the voltage here will be equal to 1/2 of 10 volts, so that's 5 volts. We also know that the voltage here will be equal to, so this is one confusing thing they do in the book. They write 6, and then they assume that it's in milliamps. It's really 6,000 ID would give you the voltage. And then here we have 10 minus 6,000 ID. I really dislike it when they do that. Anyway, so we're going to talk about those equations in more depth, but you can see this is a problem that you can kind of eyeball it. All right, so note that because the relationship between the gate and the drain is capacitive, this is essentially a capacitor right here with a dielectric material in the middle, no DC current will flow through the gate and IG is equal to 0. So we can very easily and quickly solve for VG, which will give us 5 volts. Note that because VGS is positive, the transistor will be active and conducting. This is an enhancement type NMOS transistor. And so, right, we know that'll be when there is some channel formed. We don't know if it's in triode or saturation region. So again, we still are going to ask ourselves, you know, what equation are we going to use? We got to figure that out. So in order to determine the triode versus saturation region, we need knowledge of VOV. Unfortunately, we don't have that. So the only solution, this is the same solution we used 2 problems back, is to assume the region of operation, solve, and check for the consistency. We're going to start off assuming it's in the saturation region. All right, so if we assume that it's in saturation region, equation 517 will apply. ID is equal to 1/2 Kn prime aspect ratio VOV squared. And, right, we can take that value and sub it in down here. 5 minus 6,000 ID. Again, I don't like it when they do that with the 6. And, right, so we define the ID expression. We cannot solve for ID because VGS is unknown. However, what we can do is we can take this expression for VGS, plug it in back here, and it'll give us a new form of 517 that is only a function of ID. So we essentially get rid of VGS by making that substitution. So we're going to plug in the values and solve for ID using the quadratic equation. So we calculate that, and what we end up with is ID is equal to 0.5 milliamps or 500 microamps. And then what we can do is use those to calculate both our VS and our VD, right? Our VS is equal to ID times 6,000. Our VD is 10 minus 6,000 times ID. So now we have our value of VS, which is 3 volts. We have our value of VD, which is 7 volts. And lastly, we got to check if we are in the saturation region. And the answer is, you'll see right here, the answer is yes. I'm going to ask you as one last thing to do here is to check that and double check my work and see if you understand why it is in the saturation region, and that means we can move on. So next time, we are going to pick up with some more examples, and then hopefully talk more about how the transistor, the MOSFET, can be used to make an amplifier.